This is a tutorial on the atom. In particular, we'll be talking about subatomic particles, isotopes, ions, average atomic mass. Start with Dalton's atomic theory from 1808. He said that an element is composed of extremely small and indivisible particles called atoms. We know modern scientists tells us we can split the atom, but then he didn't know that in 1808, obviously. And if you split the atom, it's no longer that atom, it would be a series of subatomic particles. All atoms of a given element have identical properties and differ from that of other elements. That's certainly true. Elements do have distinct properties that are somewhat unique. Atoms can neither be created nor destroyed or transferred into atoms of another element. We know with modern science, again, that's not quite true, but in terms of ordinary chemical reactions and things you do in an ordinary general chemistry lab, that is certainly true. We get into nuclear science and start doing all sorts of fancy things and supercolliders and all that stuff. That's certainly possible. Compounds are formed when atoms of different elements combine with one another in small whole number ratios. Certainly true. Again, modern science has proved some of this to not be correct, but in terms of ordinary chemical reactions like you'll see in most of general chemistry, with the exception of a nuclear chemistry chapter, these statements are true. And we also find that the relative number and kinds of atoms are constant in a given compound. That is, every time you form that compound, you have the same number of each type of element. And you can certainly combine them in different amounts and form a different compound from the same elements, but every time you form a given compound, the ratio is the same. And that's certainly accurate. The atom is the smallest particle of an element that can have a stable, independent existence. Yes, we stated we can split the atom, but then it's no longer that element. Or certainly it's no longer an atom, because you got a bunch of subatomic particles. Two or more atoms bonded together form a molecule. Here are some examples. You got N2, O2, S4. All those would be examples of molecules of an element, because they're all the same element, so those are still elemental forms of those things, and therefore they're molecules, but they're certainly elements as well. You got H2O, water, NH3, ammonia, C12H22O11, which is table sugar or sucrose. Those are two or more different kinds of elements forming a molecule, and we call those compounds. And we'll talk about it a little bit more later, but that's the essence of it. We got protons. They're in an atom. We got three types of subatomic particles. Protons, positive charge. We got electrons, which carry a negative charge, and neutrons, which are uncharged. And those are our three basic subatomic particles. Yes, can you split those particles up and get things like quarks and things like that? Yes, but that's beyond the discussion we're trying to have here. Protons and neutrons are located in the nucleus of an atom, which is small in terms of volume. Note, most of the mass of the atom is due to the nucleus. So the nucleus doesn't occupy a very large space, but it does have a large mass on an atomic scale. There can be variable numbers of neutrons for the same number of protons. Now the protons tell you which element it is you're talking about. You change the number of protons, you change the element it is. But you can change the number of neutrons and slightly alter the mass. When you do that, you get isotopes. They have the same number of protons, meaning they're the same element, but different numbers of neutrons. Now electrons are located outside of the nucleus, and most of the volume of an atom is due to the electrons swirling around the nucleus, but they're very low mass, but they occupy in total a large volume. And again, there can be variable number of electrons for the same atom as well, as long as the protons are the same. Since their number of electrons are no longer equal to the number of protons, however, since protons are positive, electrons are negative, that's going to cause the atom to be charged. And if it's charged, we call that an ion. For example, an atom loses electrons because you only lose or gain electrons. You lose electrons, you're going to have more protons than electrons, and so it will become positively charged. For example, sodium loses an electron, it becomes sodium with a +1 charge. Positively charged ions are called cations. When an atom or molecule gains electrons, it would become negatively charged though. For example, when chlorine gains an electron, it becomes chloride. And negatively charged ions are called anions. And you can lose or gain more than one electron. Since the sodium is +1 and the chloride is -1 on terms of the charge, oftentimes we omit the 1 and leave it as sodium plus or chlorine with a minus charge. And so the absence of a number will imply a 1. This is just a diagram of the atom showing the electrons occupy that blue shaded region that's larger, and then sort of the darker blue there would represent the nucleus where the protons and the neutrons are. Certainly electrons are occupying a larger volume, or this is definitely not to scale, but it serves to show the basic idea. Now, all atoms will have an atomic number, often symbolized by Z. That Z is equal to the number of protons in the nucleus. The atomic number is given that symbol Z. Now that Z is the uppermost number in each element's box on the periodic table. The atomic number does determine, as we've mentioned, the identity of the element. Elements would differ from one another by the number of protons in the nucleus. Other particles can vary, but protons have to be the same for it to be a particular element. If the atom's neutral, the number of electrons will equal the atomic number as well. But if you have an ion, it will not. The mass number, or A, is the sum of the number of the protons and the neutrons. Because the mass is determined by the protons and the neutrons, the electrons are relatively low mass and are considered negligible in terms of the total mass in many cases. Now, Z is the proton number, and we call N the neutron number. Then we say A, the total mass, is equal to Z, the number of protons, plus N, the number of neutrons. That would give us the mass number for the particular element. Common way to show that, where you got the mass number and the proton numbers, is where E is the symbol of some element. You write A as a superscript over Z, which is a subscript, which is a generic way to write the elemental symbol indicating which isotope it is. You can also shorten that by omitting the Z, since I can get the atomic number from the periodic table using the atomic symbol. To express that verbally, we just state the name of the element, place a hyphen, and then list the mass number, because that will tell us which isotope it is, and we can get what information we need from that. Here is a periodic chart square. At the top, you'll see the atomic number. This happens to be carbon. So it's element number 6, so that means it has 6 protons. The symbol is C. And that number at the bottom is the average atomic mass. Now that's the average of all of the naturally occurring isotopes, and should not be taken as the mass of any particular isotope. Here are a few isotopes and examples of the notation as I mentioned before. So we got 12, 6 carbon, so that's a carbon. We call it carbon 12. Notice we got 12 and 6 next to the symbol for carbon in the first column. In the second column, we've omitted the 6. And in the third column, we just write the word carbon, dash, and then 12 for the mass number. You can see very similar thing for phosphorus in the second column. We got 31 over 15p. And then the second column, we just omit the 15 because we can get it from the periodic table. And then we write phosphorus 31 as sort of a verbal representation. Third row, we've got nickel with a mass of 58, atomic number 28. And so in the second column, we eliminate the 28 because we can get that out the periodic table. The last column, we just write nickel 58. And so that's the ways that the isotopes were commonly referred. Here are some isotopes of neon. Now, not all isotopes of a particular element that naturally occur equally. You'll find for neon, most of the neon occurs as neon 20. And most of the rest of it will be neon 22. There are only trace amounts of neon with a mass of 21. And if you look at the periodic table, you find that the average mass of neon is 20.18, which is very close to the 20 isotopes. So you find that the average will lie much closer to the isotope that is most abundant. And so this is a weighted average and not an even average. And I'll show you in a minute how to average some of these out. Here are all the neon isotopes. Here we got neon 20, neon 21, neon 22. You notice the proton column, they all have 10 protons. And in the last column, they all have 10 electrons. What you see as varying is the number of neutrons. Neon 20 has 10 neutrons because 20 minus 10 is 10. Neon 21 has 11 neutrons because it takes 10 plus 11 to equal 21. Neon 22 will have 12 for very much the same reasoning. 10 plus 12 is 22. And so that's the number of protons, neutrons, and electrons, assuming a neutral atom for neon. So let's determine number of protons, neutrons, and electrons in each of these isotopes. If we got oxygen with a mass of 16, we can see that bottom number is an 8, so we know we got 8 protons. The neutrons, we're going to take that mass number, we're going to subtract 8, and so we'll have 8 neutrons. And then, since I'm showing no charge, the number of electrons equals the number of protons, which equals 8 in this particular case. Let's look at one that's a little bit more difficult, uranium with a mass of 238. So we can see the 92 there on the bottom. It's element 92, so 92 protons. Now the neutrons will be 238 minus 92, or 146. And again, since it's neutral, the electrons equal the protons, which equals 92. And let's look at the chloride ion. It's got a -1 charge showing there in the upper right-hand corner. The rest of it will work the same. Number of protons is 17, because that's the bottom number. Number of neutrons is 35 minus 17, or 18. Now the electrons is what's going to be different. Number of electrons will be 17 plus 1, which is 18. We add 1 electron even though we have a negative charge. Because remember, electrons are what we're adding or removing, and electrons are negative. So we're going to add 1 electron because I have a -1 charge to get my 18. Now, here's one with a positive charge. This is silver with a mass of 108, and I've given it a +1 charge. Number of protons, 47. Number of neutrons, 108 minus 47, or 61. And the electrons, we're going to make a very similar argument, but since it's positive charge, we'll go in the opposite direction. Electrons will be 47 minus 1, because I have to take away an electron to give it a positive charge, which will give us 46. Now, atomic mass units. Typically, the atomic mass unit is defined as exactly 12 atomic mass units for a carbon-12 isotope, abbreviated AMUs. And so if we use that as our reference, we can come up with the atomic weight scale for other atoms. So we're defining it as being exactly 1/12 the mass of a carbon-12 by definition. So that's 1 atomic mass unit. So the mass of 1 gram in AMU would be 6.022 times 10 to the 23rd AMUs would equal 1 gram, which that number should look very familiar, and it's Avogadro's number. So that's a very convenient relationship that we'll use to our advantage later on. Now the average weight of an element is the weighted average of the masses of the stable isotopes, and these isotopes have to naturally occur. These isotopes are going to naturally occur to be counted, and they have to be stable. Elements on the periodic table that have parentheses around them, and you don't usually see decimals, those are ones that are not very stable, and what they're listing is the mass number of the most stable isotope. And those don't represent a weighted average, but the others do. So that bottom number in each element's box is the average atomic mass, but we want to ultimately show how that's being calculated. However, do not confuse that with the mass of any particular isotope, because the mass of any given isotope will not necessarily equal the average, because there's more than one naturally occurring isotope for most elements. So let's look at an example. Naturally occurring chlorine exists in 2 particular isotopes. There's 75.77% of its chlorine-35, and that has a mass of 34.97 atomic mass units, and 24.23 of it is chlorine-37, which has a mass of 36.97 atomic mass units. We're going to calculate the average atomic weight of chlorine to 2 decimal places. So what you really want to do is take that percentage, convert it to a decimal, and multiply it by the mass of that particular isotope. And that's what we've certainly done here for the first one. 0.7577 times 34.97 atomic mass units equals 26.50 atomic mass units. The other isotope, 24.23, coming from the 24.23%, times 36.97 atomic mass units will give us 8.96 atomic mass units. Adding those two together will give us 35.46 atomic mass units. And considering I truncated to round to 2 decimal places in a couple of spots, that is pretty close to what the mass is on the periodic table. And so that's what you should get if you're dealing with naturally occurring percentages from naturally occurring isotopes for a real element. The answer should be what's on the periodic table. If not, something's gone wrong. This has been a brief tutorial on atomic structure and subatomic particles.